Hello everyone, welcome to my channel. This is Lin Yan. In this presentation, I will introduce current EV battery heating and cooling technology. Battery thermal management plays a very important role in battery heating and cooling. Firstly, it can ensure battery operation under optimal temperature range and lower the temperature spread within the battery. Secondly, it can monitor the state of the battery and be able to detect the critical point of battery failures and deliver alert messages. Finally, as soon as the thermal hazard happened, the treatment can suppress thermal runaway propagation effectively. Let me explain a little bit about thermal runaway. As the graph showed, thermal runaway describes a process which is accelerated by increased temperature, in turn releasing energy that further increases temperature. If the temperature is out of control, it may lead to self-ignition and even explosion in some cases. The performance of lithium-ion battery cells is greatly impacted by their temperature. They do not perform well when too cold or too hot, which can lead to permanent and extreme damage of the cells or accelerated degradation. When the battery is too cold, low temperature effects mostly take place in high latitude areas, such as Russia, Canada, and Greenland Island. In these areas, the outdoor temperatures in winter are much lower than 0 degrees C. The battery cell's internal resistance rises as temperature decreases, which will affect the performance and life of lithium-ion batteries. At temperatures below 5 degrees C, most lithium-ion batteries cannot be fast charged. At temperatures below 0 degrees C, the batteries lose charge due to slower chemical reactions taking place in the battery cells. The result is a significant loss in power, acceleration, and driving range, and higher potential for battery damage during charging. What if the battery is too hot? Compared to the low temperature effects that are mostly limited to the low temperature application environments, the high temperature effects happen in a much broader range of applications, including not only high temperature environments, but also low temperature environments. Most of the time, high temperature effects are due to the high internal temperatures of the lithium-ion batteries during operation, rather than the environmental temperature. At temperatures above 30 degrees C, the battery performance will degrade, posing a real issue if a vehicle's air conditioner is needed for passengers. The result is an impact on power density and reduced acceleration response. Temperatures above 40 degrees C can lead to serious and irreversible damage in the battery. At even higher temperatures, example 70 to 100 degrees C, thermal runaway can occur. This is triggered when the runaway temperature is reached. The result is self-heating chain reaction in a battery cell that causes its destruction while propagating to adjacent cells. The ideal temperature range for an EV's lithium-ion battery is about 20 to 30 degrees C. To keep it in this range, the battery temperature must be monitored and adjusted. A battery thermal management system is necessary to prevent temperature extremes, ensure proper battery performance, and achieve the expected life cycle. An effective battery thermal management system keeps cell temperatures within their allowed operating range. Heat sources of the battery. As ever faster battery charging rates are demanded with recharge power of over 200 kilowatts to deliver times of 30 minutes or less, higher performance electric vehicles with a requirement for consistent performance and adequate durability in global markets has meant that special thermal management methods for the battery pack are required. In EV batteries, current flow, both charge and discharge, generates heat inside the cells and in their interconnection systems. This heat is proportional to the square of the flowing current, multiplied by the internal resistance of the cells and interconnect systems. Q equals I squared times R. The higher the current flow, the more the heating will be produced. Battery manufacturers and researchers routinely investigate how the rate of heat generation in cells varies over the course of charging and discharging. Heat can be generated from multiple sources, including internal losses of joule heating and local electrode overpotentials, the entropy of the cell reaction, heat of mixing, side reactions, and so forth. We also need to monitor the thermal spread inside the battery, since temperature variation from module to module within a pack also can lead to electrical unbalance, which affects battery pack operational performance. Various cooling agents and methods are in use today as part of thermal management of EV batteries. Among these are air cooling, liquid cooling, refrigerant cooling, and others. By air, an air cooling system uses outside air and the movement of the vehicle to cool the battery. Fans and blowers are often added to enhance the cooling effects. By coolant and air, the battery can be cooled by circulating cold coolant to it. The coolant will carry the heat from the battery and then be pumped to an air-to-coolant heat exchanger, such as a radiator, to dissipate heat to the outside air. These two methods are usually not enough to cool the battery when the ambient temperature is too high. Say the outside air is 40 degrees C and we need to cool the battery down to 30 degrees C. So here comes another method, battery air cooling coupled with HVAC. It takes advantage of the heat exchangers from the HVAC system to regulate the battery temperature. This innovative design of battery thermal management cooperative with vehicle climate control system has been presented by Toyota, Ford, and Honda. By refrigerant. Refrigerant direct cooling or direct expansion uses the same refrigerant such as R134A, R1234YF, etc. as used in your vehicle's air conditioning system to cool the battery directly. The liquid glycol is eliminated in the battery pack. Refrigerant direct cooling offers cooling rates 3 to 4 times higher than liquid glycol. By coolant and refrigerant. The battery can be cooled or heated by circulating coolant to it. This method is one of the most popular methods to cool the battery, which is typically called liquid cooling. When the battery needs heating, the coolant will absorb heat by a heat exchanger. For example, an indirect condenser or an electric heater, and then go to the battery to heat the battery pack. When the battery needs cooling, the coolant will be cooled by a different heat exchanger, for example, a chiller, and then be pumped to the battery to cool the battery pack. Note, the heat exchanger can be bypassed if it is not needed by adopting a three-way valve. Liquid immersion. The battery can also be regulated by immersion in a secondary liquid. The mentioned but not limited choice of heat transfer medium, including air, liquid, phase change material, or any combination, has a significant impact on the performance and cost of the battery thermal management, which has its own limitations and merits. In the following slides, I will give some examples of current EVs using these 4 cooling methods: air cooling, liquid cooling, refrigerant cooling, and liquid immersion. Okay, let's first talk about air cooling. Air cooling is advantageous in its simplicity and low cost. It eliminates the need for cooling loops and any concerns about liquids leaking into the electronics. The added weight from using liquids, pumps, and tubing is also avoided. The major disadvantage of air cooling is its inefficiency. Even with high-powered blowers, air cooling does not transport the same level of heat as a liquid system can. This has led to problems for EV in hot climates, including more temperature variation in battery pack cells. Blower noise can also be an issue. Still, air cooling solutions have their roles and value. Commercially, Nissan Leaf, Honda Insight, Toyota Prius, Renault Zoe, and Hyundai Ioniq utilize air cooling of their battery systems. This picture shows the Nissan Leaf battery pack, which is cooled by air. And this picture shows the air-cooled battery thermal management system used in Toyota's Prius. You can see the blower here pushes the ambient air to cool the battery more effectively. Liquid cooling. Liquid cooling. Liquid has high specific heat and thermal conductivity than air, so it can mitigate battery temperature rising and prevent battery overheating more effectively than air at the cost of a more complex system. They are the production vehicles using liquid cooling. It is the prevalent cooling technology in the industrial application nowadays. In this slide, I will show you 3 examples of liquid cooling technologies applied to production EVs. Tesla. Tesla was one of the first to announce a high-performance sports car with the release of Tesla Roadster. High-performance requirements mean their cooling system also had to be top-notch. Tesla has come up with a unique method to cool their thousands of cylindrical cells located in the chassis. This is a Tesla patent describing Tesla uses a metallic cooling tube that snakes through the EV battery pack. This flexible tube provides direct cooling by maintaining contact with the surface of every cell. As can be seen from the picture, a thin layer of polymer material also separates the cooling tube from the battery. This picture shows the battery pack of a GM Chevy Bolt, which is liquid-cooled via a base plate below the cells. GM's Chevy Volt features a liquid cooling system to manage battery heat. Each rectangular battery cell is about the size of a children's book. Sandwiched between the cells is an aluminum cooling plate. As seen from the picture, there are 5 individual coolant passes passing through the plate in parallel to enhance heat transfer effectively. Each battery cell is housed in a plastic frame. The frames with coolant plates are then stacked longitudinally to make the entire pack. Refrigerant direct cooling. Refrigerant direct cooling or direct expansion uses the same refrigerant as used in your vehicle's air conditioning system to cool the battery directly. The liquid glycol is eliminated in the battery pack. Refrigerant direct cooling offers cooling rates 3 to 4 times higher than liquid glycol. These EVs use refrigerant direct cooling. For example, BMW already has such a system in the i3. Here is a freeze frame of the refrigeration cooling tubes being installed in the bottom of the aluminum battery tray at 28 seconds into this BMW Group video. The batteries are then placed on top of the cooling tubes. Per the words of Muro and Associates at 2 minutes into this YouTube video, this is the easiest heating and cooling system I've ever taken part in 30 years. BMW i3 equipped with expansion valve and globe valves to operate independently the fluid overheating degree and import-export respectively. After the expansion valve, the liquid or partly liquid refrigerant will flow into the evaporator to cool the battery directly via a lot of evaporative latent heat. I won't explain this system in detail in this presentation, but if you want to know more, comment below and let me know. While most major OEMs in the passenger car market are utilizing air or liquid cooling methods, some suppliers are turning to new methods to meet the increasing thermal demand of vehicle batteries. This is especially true when considering more specialized markets, such as electric construction and mining vehicles. In this scenario, extremely intense battery discharge is required, and hence a serious amount of heat is generated. Immersion cooling is one of these emerging technologies for battery thermal management and has been previously demonstrated in electronics for data centers, high-performance computing, and grid power systems, but is now seeing an opportunity in the electric vehicle market. As the name suggests, immersion cooling involves submerging the battery cells in a liquid coolant. In doing so, superior thermal contact homogeneity can be achieved. Additionally, the flame retardant nature of the fluids acts as a safety feature, suppressing thermal runaway events before they propagate between cells. A key consideration here is obviously the choice of coolant fluid used. Through primary research, the current flow options include those from 3M, Solvay, M&I materials, and engineered fluids. These fluids are all dielectrics but vary in their properties with factors such as weight, thermal conductivity, environmental considerations, and cost being extremely important. This is a fluid immersion system demonstrated by 3M. We can see the batteries are submerged in its Novec fluid, which is circulated in a loop to be heated or cooled. XING Mobility is a company specializing in the more niche electric vehicle markets with their modular immersion-cooled battery packs utilizing 3M's Novec fluid. The picture showed the immersion battery cooling system developed by XING Mobility. If you are interested to know more about the details, I recommend you to watch the YouTube video. I will put this link below the video for your information. In another niche market, Rimac Automobile has opted for Solvay's Golden Fluid for their electric hypercars. While the technology shows promise with technically excellent performance, it will be difficult for immersion cooling to enter the mass production automotive market due to the increased weight and cost compared with currently utilized methods. However, regulations regarding thermal safety of electric vehicles are changing, and with it, this emerging technology may start to take a more significant market share. To compare the top 3 cooling methods and conclude. Air cooling. Air cooling, because of a small heat capacity and thermal conductivity of air, even with high-powered blowers, does not transport the same level of heat as a liquid system can. This has led to problems for EV in hot climates, including more temperature variation in battery pack cells. Air cooling system is much simpler than liquid cooling system, since it eliminates the need for cooling loops. The added weight from using liquids, pumps, and tubing is also avoided, so air cooling system is much cheaper. Air cooling eliminates the concerns about liquids leaking into the electronics, so it is the safest. However, in respect to control, other than changing air speed of the fan, there is little control over heat dissipation. Liquid cooling. Compared with air medium, liquid has a higher thermal conductivity and a higher heat capacity, which behaves better in the temperature distribution of battery pack. Liquid circulation cooling usually behaves better in temperature controlling and uniformity. Battery thermal management with liquid circulation loop also has some inconvenience in its complexity structure with some accessories, heat exchanger, pump, etc. As for the aforementioned liquid cooling, the first coolant loop for battery is usually connected with the secondary refrigerant circulation loop, with the joint of the intermediate refrigerant to coolant heat exchanger, which adds weight and complexity of the system. Also, coolant cooling has potential in leakage. For liquid cooling, we can control the coolant flow rate, the secondary medium temperature, mass flow, and others. It can satisfy various thermal controlling requirements, not only for battery, but also for power electronics and electric motor subsystems according to different temperature control demands with a multiple fluid loop mechanism. In conclusion, it has become the prevalent cooling technology in the industrial application because of its flexibility in integration and precise control for heating and preheating. Refrigerant cooling. Refrigerant direct cooling with boiling heat transfer has several significant advantages in higher heat fluxes with evaporative latent heat, better thermal homogenization for temperature uniform distribution, and a compact structure with eliminating a pump mechanism, as well as a more rapid thermal response compared with conventional battery thermal management. Therefore, it can be an excellent strategy for a high necessity of battery thermal safety. Additionally, it also can be applied to battery thermal safety synergy control for its potential in emergency cooling of spraying and prevention overheating or thermal runaway propagation. It means that refrigerant-based direct cooling should develop a cross-coupling controlling strategy to realize a synergy control both for battery thermal management and battery thermal management with enhanced safety. As concluded, refrigerant direct cooling allows higher charging power, reduced complexity, potentially reducing costs, and has the added safety advantage of getting liquids entirely out of the battery pack. That's all for battery cooling and heating technologies. If you feel that this video is somewhat helpful, do not forget to give me a thumb up and subscribe.